let me go ahead and quickly introduce the subject and then introduce our guest speakers, and we'll get going. So today we're going to be talking about really an outshoot of what we see in the industry as the impact of low computational resources. One of the key things that we're noticing is unlike previous generations where looking at one high-fidelity simulation could perhaps take a graduate student their entire career, we're now finding people are using high-fidelity simulation much in the way that they might use a wind tunnel. And that includes actually hybrid methods where we'll talk about that today a little bit, where people are using low-fidelity simulation with surrogate models to apply high-fidelity simulation to model system performance. And what we've been working on here at Tecplot is really coming up with a solution for simulation analytics, which is really bringing together the analytics piece, which is new, I think, to this arena, physics visualization and data management, into one tool which allows you to analyze system performance. I'm not going to spend a lot of time on this outside to say that Tecplot Chorus is an application which was designed as a framework to help people really look at collections of simulation results as well as simulation and test results. And that's about all we're going to talk about in terms of tools today. That's really not what we're here to talk about. We are joined today by Dr. Ryan Starkey from the University of Colorado. Ryan received his PhD from the University of Maryland, where he studied air-breathing hypersonic missile configurations with external box constraints. And he also did his master's work there on a parametric study of L/D and volume efficiency trade-offs for wave rider-based vehicles. He is currently the CEO of Starkey Aerospace Corporation, as well as an assistant professor. And I believe we're going to be turning it over to Ryan, and he's going to be telling us about some of the work he's done with using these collections. And so I'm going to turn it over to Ryan. Ryan, good morning.
Good morning, everybody. Thank you.
I'm also joined by our CTO, Scott Imlay, who will be sitting shotgun as we go through the conversation. Morning, Scott.
Good morning, everyone, and welcome, Dr. Starkey.
Thank you. Thank you, everybody, for tuning in today. I know everybody's busy. Let me just first say, this is a collection of work probably done over a number of years by hordes of graduate students, undergraduate students. I get to kind of sit at the end and out-report on a lot of great things that go on here at the University of Colorado. So my intent is not to make it seem like we churned this overnight and made it really simple and trivial, but there's a lot of work that's gone into this. So today we're going to talk about, as was mentioned, system performance analysis, looking at highest fidelity simulation and how do we embed that and understand that as it implies for design. Obviously, as was mentioned, design is getting more and more complex, and there's lots of things that go into a rigorous analysis. As a university professor, we also really embrace engineering fundamentals, kind of back the envelope textbook level analysis. And so how do we kind of bridge those two extremes when we talk about design? So the overview for today's talk is kind of some of it may be a review for many of you who are involved with design work, so I apologize for that. We won't labor on some of the really simple points, but just understanding systems development, what it means, kind of thinking in the big picture context, looking at surrogate modeling, a couple of different examples of how we may apply surrogate modeling and kind of why it's important, and then roll that back up into how that kind of bridges those gaps for multi-fidelity data. So the low fidelity, as we like to kind of do a really good preliminary level design, we want to do low fidelity data. Obviously, eventually, we're going to need to use a lot of high fidelity data, and putting them together inexpensively is always the goal. And then we'll kind of wrap it up with going over an application of a supersonic UAV we've been developing here for the last number of years, and then kind of maybe draw some conclusions from it. All right, so I guess the context first is important. Is why are we interested in this? Obviously, multidisciplinary design optimization theory is great, and we do a lot of work in the fundamentals of that, as you'll see. But without a goal, students sometimes get lost. So we try to have both here. The vehicle we've been working on, you see here in the picture, we call small, sleek, and supersonic. Right now we're small and sleek. Until we fly, we're not supersonic yet, but we'd like to think we are. But the goal is to design something capable of achieving Mach 1.4. So again, we're trying to apply some very aggressive design goals here that we're going to use our tools with. Aircraft mass of under 50 kilograms, and that is really set by a desire when we started on this problem by the students. When we decided to set a world speed record, at least that was the goal. There's a 50 kilogram or less category and a 50 kilogram and up to 500 kilogram category, so we decided to be light. Not saying we can't be heavier, but that's our current target. And then, of course, inexpensive. So if we want to be a flight test platform, we need to be something where if you're testing new technology and something unfortunate happens, you haven't lost your entire budget. You can build another one and keep flying. So the goals on the university side you see on the bottom there are technology test bed, things like sonic boom minimization research, science missions such as storm approach and penetration, and of course, anytime you can go fast, there's other tactical sort of missions. So kind of boiled a whole lot of different things into one vehicle, and we're trying to embrace that as we go through our design study. Okay, so the basics of what this I'm sorry, I'm having a controls problem here. Oh, there we go. Do you still hear me? Hopefully. The basis of what this looks like is a takeoff and landing, a cruise portion, a turn, a cruise, and another landing. So, the way that we approach this, at least from the student standpoint, is important to embrace the notion that we are designing a complex aircraft system that is not unlike other, obviously supersonic aircraft. We're trying to do it with a very small team. It's a team of students who are essentially learning as we go, both discipline and kind of engineering, system engineering as a guiding principle. So we have a lot of design challenges, and we don't have a team of experienced engineers with a lot of tools that they've used for years. We're kind of learning and training as we go. And so obviously to go through this sort of mission with the supersonic leg in the middle is not a trivial endeavor. So this is essentially our guiding principle of what we're trying to do, and we'll refer back to this later on at the end when we try to kind of tie the tools back to this goal. So let's take a minute now and go through some systems development and understand, at least from the tool standpoint, why what we're talking about may be a really important way to embrace design. I'm sure you've all seen charts of very similar nature to this one, where we kind of go through that top bar and that bottom bar, looking at different trade studies, testing, analysis. There's so many different disciplines, so many different components, propulsion, aeroelasticity, internal aerodynamics, external aerodynamics, antenna systems, where we have to do testing, both computational testing, we have to do physical testing, and then wrap it all together to get a vehicle design. And so, notionally we look at aircraft that we see today, maybe an F-22 or F-35, and kind of think back to the decades that we've taken through both propulsion system, aerodynamics, and putting it all together. It is a long, complex, expensive endeavor to come up with a new aircraft design. So obviously, in the classroom and in the university setting, we're not going to go through that. We don't have 2 decades. We're happy to get their attention span for 50 minutes. But if you look at through, of course, the middle block, this is the problem that we always have. There's more conceptual designs that we can even maybe generate and or analyze. And so how do we go through this really simple design analysis? How do we break that down, boil that down to a couple of conceptual designs that we may want to focus on? And of course, this is easier to do. Sometimes the conclusions that link those 2 stages are not correct, but we can always down select from a lot of designs to a few designs. But inevitably, we need to go back to those conceptual designs, move through preliminary details, and throw a lot of tools at it. We need to throw a lot of the tools that are listed here on the top and bottom to an aircraft configuration. Of course, any other complex design system has got its own similar set of tools and analyses to get from a simple design, a preliminary, conceptual design up to a detailed design. And so the real question we're trying to answer is, how do we do this most efficiently? Obviously, if we have a lot of computer power, we can throw a lot of resources at it, and we can We can churn a lot of simulations and hope that'll work. So what the goal of today is to kind of maybe bridge that gap. We're saying those are still important, but we need to think a little bit differently. So wrapping kind of what you see here on this chart into maybe a software architecture, things get a little bit more complicated. Picturally, looking at the pictures, we can understand why these things are maybe interesting, challenging, difficult. Even if I'm just a student who's focused on our one particular thing, this is my one particular area of expertise. But eventually, everything has to essentially talk together, work together. Tools need to be integrated. Sometimes they're loosely coupled. Sometimes you can use much more elaborate software to couple them, depending on your desires and your budget, really. But so this is a sample architecture for a high-speed vehicle design, and the same thing exists of really any vehicle design. So I continue to use this as a great example, but there's a design part, there's trajectory part, there's in case of high speed, and even for ours going supersonic, there's parts that require thermal protection, especially around our afterburning engine. Structural sizing is a really traditionally hard thing to do in a conceptual level design and preliminary level design. Aeroelasticity, again, a difficult component. Control systems. We wrap this all together and we try to come up with a vehicle. And generally, the way that this happens, I would say notionally, is low fidelity. So somewhere we need to talk between low fidelity or high fidelity and how to bridge the gap. So the gap is really the surrogate modeling. How do we understand surrogate modeling? How do we put the pieces together where we can have a surrogate model that takes our complex data set and reduces the number of data points that we really need to run so we can do a good job of minimizing our computational expense while still extracting the most usable information from our system. So the surrogate modeling, obviously, oops, I've lost control. There we go. There's a lot of kind of driving goals of what we're trying to do with surrogate modeling. That tell us what we're trying to do. So obviously, when we're looking about a complex system design, this quote that's here is really good. We want a system that is insensitive to small changes and uncertain quantities, and insensitive to some acceptable probability of failure. So obviously, we want reliability to be in the 4 nines or some other really extreme number, which means we need to do uncertainty analysis, uncertainty quantification. And we're not going to spend a lot of time talking about that here today, but reliability-based design optimization fits into the same flavor that we are talking about with the modeling. So we want to obviously predict system performance, widespread performance, using a few or minimal set of data points. And so, the extreme example I like to really use is, a high fidelity, say a large eddy simulation, CFD code that might take on a complex case, running in parallel, days, week, I don't know, depending on how much computer resources you have. It takes some considerable amount of time. Well, what happens if I want to do a wide understanding of my design? I need to run those cases to an excess to understand the design limits, high angle of attack, high angle of side slip, altitude changes, Mach number changes, etc. Well, what happens if I want to do that same level of trade study, or say the same level of understanding while I'm changing my vehicle configuration? Then it becomes, essentially this, what's commonly called the curse of dimensionality. We all of a sudden have too many perturbations on the vehicle, too many perturbations on design features and performance features where we can no longer run it all. Even if we wanted to run it all, we couldn't run it all, and we definitely, obviously, do not want to run it all. So, as mentioned here in the bottom, if you're really especially interested in combustion problems, the computational time is much more to the extreme. And of course, the uncertainty involved with that is also another issue that we're not going to really dwell on here. But the computational cost when we want to understand vehicles, vehicle system, vehicle performance, vehicle design, as I'm sure everybody's well aware, is a challenge. So let's make sure I have control here. So how we address that challenge is through the surrogate modeling. Surrogate modeling, what you see here is a really crude diagram on the bottom corner of just some system where there's some maximum, some minimum, a number of discrete places where it's not just a linear, simple design space. We have a complicated space. And what you also see on there are some starred points, some places where we actually physically ran data, trying to understand what was going on. And from that, we want to build a model of what the entire system response may look like, even though we haven't run all the data. So if you're not familiar with surrogate modeling, really it's another just really what I call exotic curve fit meta modeling. You might hear a lot of different names for it. But what it is just a way to take a few data points and extrapolate it to a larger design space. So different models are definitely available, and I think if you search the mathematical literature specifically and some of the design literature, you'll see differences for coarse or fine systems where how many data points I need. Are they ordered data points in a structured sense, or are they randomly distributed around a design space? Different models handle different constructs better and or worse. And of course, the goal is how do we use only a few data points for a large dimensional space to capture the physics. And of course, then the other question that we have to answer is, we're going to come up with run a few data points, and maybe each one of these took 1,000 CPU hours. I don't know. Run a few data points and then try to understand how that relates back to our system, but with the question of, is our model that we're generating even correct? So obviously, if the model is not correct, we're using it in a very dangerous way, because we're going to use it to predict design. So there's a couple of different things that have to go here. We can't just black box approach, put some data points into a generator, come up with a model, assume it's correct. We have to essentially go through this test. And for anybody who's done something like a design of experiments, which is essentially an optimal approach to distributing your set of data points to minimize your costs, such as a Latin hypercube approach, these are very good places to start with a data set. We want to minimize the number of inputs, distribute it around our design spaces as optimally as possible, at least initially, and use that as a good starting place. And so that's what we will do. And so the example that I have here that I'm going to show you is a model called Kriging. Kriging has been around for a long time. Kriging was originally designed to be a very structured surrogate model for a very structured data set based on very structured inputs to come up with a model. Inevitably, what we want is for our data set is to understand, and it looks like the graphic here is a little bit hazy, but you see an actual function here. So this is what we're actually trying. This is the system that we actually hope to achieve, is this grayish line. The dashed line is a surrogate model based on what you see there as 4 input points. So we picked 4 input points, and of course this is a linear example, and the function is on the bottom, so it's really easy. But this is the danger of any sort of curve fit. Really, is we can fit anything. It's just how good is it is another question. So Kriging, there's definitely ways to do optimal optimal positioning of new points based on the maximum likelihood of error of the existing model. So sometimes you may extract one point, test your model to see where the maximum likelihood of error is, and then you can kind of use this sequentially to add points and keep essentially pinging your model against what you think reality is, or the pseudo-reality, and minimize the sensitivity of the model to the point addition. So in this case here, there's 4 input points. You see the model is a really poor fit. We go through a selection of another point. You see the model changes. Again, sequentially, we'll step through this a couple times. You see we're getting a little better on the latter half of the model. The front half of the model is still quite poor performance. And then as we continue to add points, we can eventually get to the correct model. And so this is the good and the bad of surrogate models. Number one, they do a great job. So here I captured this design space with finally used 7 points, and that does a great job of capturing it. And so everywhere else in between, now that I have this surrogate model or this map of our design space, I can use this map to do my optimization on, my interpolation on, whatever it is I'm trying to do. I now have a good data representation. And so the next chart is a really brief algorithm example, and so that way it's, when you maybe look back at this later on, you have a complete idea of what is going on. But we have a random input, and in this case we we literally use some random inputs because you know, I guess for this example, it stresses the data in a little bit more interesting way than using a really good design of experiments. But we select some sort of inputs, we build a surrogate, we choose some, we run our functions, at some of the surrogate points, we can validate the surrogate, we can re-add new data points, and then continue to go around this loop until we're happy with the surrogate. And so in this case, the surrogate becomes a very interactive feature with design. We need to start our design and then let the surrogate essentially drive where new data points go after that. And so this is, I'd say, the one piece maybe where it's different than maybe how education is generally done, is where we generate a lot of data and let's just fit it, hopefully that it's going to be good because we have no more data to add, we can't run another test, we're not going to run another computation, and that works fine as well. But I think the real advantage to surrogate modeling is to use it as an interactive guide. So we're going to come up with the best first estimate of our design experiments, and we're going to use that to push our design forward, while using the surrogate to drive where the next points should go. So either computationally or experimentally. Now, obviously, experimentally, once we're in a tunnel, we're going to start our test suite and just keep running until our time is used up and our money is used up. And so that becomes a little bit different test. But hopefully at that point, it's more for validating the model, not to drive the model. But both cases definitely work. So going on from here, you know, the next step is obviously if we're looking at complex system design, we want to build a surrogate. We want to understand, kind of in the same light as before, how do we build a surrogate that matches our design space without knowing where our design space is. And so the example that I'm going to show you is another, I would say, good test analytical function of a design space that makes no physical sense, but it shows you, you know, maybe if we stress this to the extreme, you know, if you look at this, you know, essentially it's a multi-sinusoidal function in 2 dimensions where there is one physical global optima and a lot of local optima, and you see it's a very jagged design space. So this is a good test. Obviously, when you look at this, the first notion you're going to have is there's no way we're ever going to build a surrogate that matches this surface. And your notion is absolutely correct. But we can use surrogates to drive us through this system in a logical sense. So again, this is where surrogates are used very much in conjunction with the data and the data analysis. So in this case, I would want to have a way to start my system, create some initial data points, and what you'll see is we're just going to do an initial random sample of 25 data points through this space and come up with a surrogate. And what you see is a surrogate that doesn't really represent the data well at all. But what we're trying to do is use the surrogate to help drive the data behavior of where should we focus in on, where's the right region perhaps, and can we use that to focus where our next series of computations are. So when we maybe do some more expensive computations or some more expensive experiments, that they're done in the closer to the region of interest that we're really going to hone in on. So in this case, 25 randomly distributed points did a really poor job, I guess if that's the correct word, of capturing this design, because there's nothing that's going to capture this design. But we use that to down select. So the system says, well then here's the region of interest. It's back here, back in this corner. So let's kind of hone in on there. We'll add in some points, and we'll do another surrogate. So now we've honed in again, and again, the surrogate does not match the space. What we're doing is just randomly populating. You see some are near the peaks, some are near the valleys, and it's coming up with a surrogate of what this system is doing. And we're going to go through this procedure again. We're going to hone in again to the back corner, So when we put it all together, what you see here is, you know, we were looking for that maximum point, and so, you know, our design was focused at that. So the error that we achieved in the surrogate at the maximum point was about 0.5%. So, you know, I'm blanking here at the number of total data points, but what we did is took a complex space, initial surrogate, and we start to build. So what you see is the final picture on the right is this compilation of all the data points for the overall surrogate. So again, it does not match the correct data space, but what we're looking for is where's that right region of interest. And in this case, it found the error, the surrogate model, the function value at that maximum point was off by 0.5%. The minimum, which we weren't focusing on, was 14%. So again, if we want more information, we need to take more data points. And we do get some X and Y errors from where our positions are. But what we are and effectively have done is gone through a very expensive, very convoluted design space with a pretty good success rate using a minimal number of inputs. And so this is really a good extreme example of where and why surrogates are helpful. Obviously, we're not going to be able to populate this whole data space with computations to map it out correctly in any event. The best we're going to do is come up with a number of good points and a data structure that hopefully represent it. So I think the good news is, especially for complex vehicle design, nothing ever looks like this. So this is really an extreme example that shows the functionality of using surrogates and surrogates for optimization. Well, let's look at another example now. Let's look forward to, here's kind of some very simple multivariate analytical. What you see is an analytical weight function down there where we're trying to do some design on, where we have 10 design variables. Again, it's starting to feel like a lot more like an aircraft design that we're talking about. Again, to stress the system and understand what it's doing. Well, this is now a function of 10 variables, not just 2 variables. So what do we do with surrogates in this case? That's really the question we're always trying to answer. We have an n-dimensional design space, and here our n is 10. As we go to more complicated designs, we're going to get away from some of these very, I'd say, simplistic design parameters to much more refined design parameters, and that's going to make that cursive dimensionality, or that overwhelming amount of data, something we're going to have to figure a way to deal with to some degree. So when we look at multiple dimensions, what we see is this. We see now we can essentially create, at least in a visualization sense, surrogates of all our all of our input parameters, all the things that drive our design. We can look at how they all correlate one to another, how they all contribute, which ones are fairly benign and linear in a sense, which ones become a little bit more nonlinear in behavior that we may need to focus our design in a little bit. So what you see, in this case here, we can take a 10 by 10 system, or we can kind of break it up into a couple of maybe where the components have much stronger interaction and start to hone in on maybe some of the more critical pieces. And so what you see on the right-hand side is the simplified version, where we take a 6-variable surrogate and a 4-variable surrogate, and we look at there, and of course the little stars on there are the data points. So again, in this case, we tested this with just a random set of data inputs, create some surrogates. What you see is some hopefully very traditionally understandable behavior interaction between some of these variables, sweep and wetted surface area, et cetera, et cetera. So there's nothing, I would say, hopefully brand new knowledge that's wrapped in here, because it's a very a very apparent problem that we're working through in terms of aircraft design, but it does show how we can now use surrogate modeling in a lot of dimensions and start to at least use that to drive the analysis. So again, the designer still has to be in the loop here. We can maybe put this in a computer and we can let it run automated, or we can do that for a while and we can stop and say, well, here's our system response. We see some very drastic behavior through some of these interactions. For instance, our vertical acceleration. So let's hone in on that one a little bit more and populate some data points that are going to help us understand that relationship better and use that to drive our design. So, if you think, extract this backwards to a complex system design, what this is going to give us is a way to understand those parameters we really want to focus in on. And of course, what we also have is maps or surrogates of our entire design space in this case, where we can now put this into an optimization routine and go ahead and use this surrogate to do our design. So surrogate models are a very powerful tool. The one way that we've been looking at doing them here at University of Colorado is, of course, now multi-fidelity. We like to start very academically. We want to start, it's very similar to the last problem. How do we understand the design problem, boil it down to its meat and potatoes, do some back-of-the-envelope calculation, which we know is prone to some error, but it points us in the right direction. And then inevitably, or like any design, we're going to want to do some validation. We're going to run some high-fidelity simulations of our low-fidelity designs and see how they calibrate. And so, that's generally, I would say, a practice that's done. What we're interested in doing is maybe kind of pointing that backwards a little more. We have what you see here is a low-fidelity data. That's kind of a standard approximation. We're going to run high fidelity data, possibly at the same data points to understand what is happening. And what we're trying to do is, what you see here in this very simplistic block diagram, is understand that error, which is what always happens in design. I come up with an approximation, I run a simulation, I want to understand how good my approximation was, which is great. I'm understanding a fine point of error. But what we're trying to do here is use surrogate models to calibrate that entire data space. So if I can kind of boil my problem down to some much more canonical, simplistic versions, which you'll see here in a second, then I can run low fidelity data, in which case ours is an analytical model. I can run high fidelity CFD data. I can understand the differences between the two. And then what we're doing essentially is mapping those differences back onto the low fidelity model. So now I have a surrogate correction to a low fidelity analytical model that's going to hopefully, give us better results. And so that's what we're going to point at here. Of course, Kriging, as mentioned here, is a way to do this as well, multiple levels fidelity. There are surrogates that are built to handle this. Our approach is a little different. We are trying to actually, as I mentioned, put our data, our understanding back to our low fidelity system. So what you see here is a analytical, and I think the results here are actually a CFD sweep of a simple a diamond airfoil problem. So interested in the diamond airfoil, our vehicle is using not a diamond airfoil but a very similar airfoil. Come up with a model for a diamond airfoil, which is it's got a nice analytical, especially, well, at least in the supersonic regime, a nice analytical model for lift and drag. Of course, it's not correct because we're missing viscous effects, we're missing separation, high angle attack, etc. So what you see here is a run of different angles of attack at a given Mach number. Go through and create a surrogate model of some of these data points, and what you see here is on point number 2 on the right corner, a structured surrogate model, or structured data input to a surrogate model. So we just do a kind of a simplistic sweep, come up with a surrogate. It looks pretty benign. It's a nice looking system. Compare this against our analytical model, and so what you see down in the bottom right corner, number 3, is a surrogate of the error. And then we push it backwards, and so number 4 is now we do some interpolation, and not of the data points that we actually tested and computed, but we're going to do some centroid points where we have no physical data. We're just going to use our models to see how well they do, and then we'll validate it with CFD. And what you see here, the errors originally are not that bad. We have some lift and drag errors for a couple of different altitudes, sea level, 5 kilometers. An Euler simulation, an Envisaged solution, an expected solution, and the Navier-Stokes, the actual CFD solution. And so in this case, what you see here is an original model, essentially our analytical model, and then the corrected model. So after we put the surrogate model back onto the low fidelity system, now we have a low fidelity, corrected low fidelity model that is still analytical, that we can run on 1,000 different design problems that is now corrected. And so this is kind of our approach to some of the more canonical parts of design. Can we build up an understanding of low fidelity systems, how they translate to errors in design, uncertainties in design, and maybe correct those where they're critical. So this is one example of, as the bottom bar says, where we can create a viscous CFD quality result using an analytical model now that we've essentially put some understanding on what's happening for this simple case. So, pardon me. Wrapping this up, surrogate models are a phenomenal tool for data space reduction, sensitivity analysis, design understanding, optimization. Inevitably, assuming that the model is correct and the correct reproduction of the actual data space is going to reduce our expense considerably. Now, of course, if the model is not correct, then it's going to send us to the wrong direction, and we're going to end up wasting a lot of time in the wrong area of the design space. Multi-fidelity approaches, there's plenty of them, similar for, as a co-Kriging, putting low fidelity and high fidelity, in our case here, training a low fidelity model, to ways to kind of approach design in an efficient manner. Now, I'm not against computational results at all. Computational results are essential. But I do have this feeling that computational results there's overemphasis on them, which says, well, we're going to optimize with some computation. It gets us an answer. We have no idea how, where, and why we got to that answer, but it does work. It's an optimal. Likely when you do optimization, unfortunately what you also get is a lack of robustness. It becomes very sensitive. And so surrogate modeling lets us fill in that gap. It lets us say, what does this actual space look like? Where's a region of optimality, and where's a region maybe of suboptimality that's less sensitive to perturbations or uncertainties that we haven't actually quantified yet. But regardless, surrogate model is an essential tool to go through complex system design. So that kind of laid the groundwork, and I'm going to spend the next 10 minutes or so going through now how we in our system, what we're looking for is this vehicle that I introduced at the beginning. How do we actually go through design? What does it mean? And now that I've kind of talked about the modeling side, the surrogate side, the design side, what have we left out? When we talk about a complex system, this is often, I would say, the part that maybe is left on the table as a lack of understanding, because there's more to it than just the design side. We have to kind of go through the whole feedback loop. So system design, I'm not expecting you to read this, but what you see is, of course, here, this is our version 7 vehicle system, and you see a lot of design parameters, and this is just kind of a summary of them. So again, this is back pointing to that cursor dimensionality. We're not going to solve it all. We can't solve it all. We need to make some good engineering judgment through a sensitivity analysis, maybe up front, as to which design parameters to focus in on. Inevitably, we're still going to need to work on all the design parameters. We'll go through maybe a surrogate modeling approach, as we saw before, looking at all the system. Which ones do we need to focus on? Which ones can we kind of put off to the side as secondary parameters and go through design? And of course, this exists in every problem. It just sometimes we maybe don't notionally go through it all in this sort of rigor. We kind of compartmentalize what we know is important, and we focus on that, and then everything else kind of fits in later. But the kind of the corollary to that is often we can get ourselves into trouble using that method if we don't really understand our system. So surrogates are essential to kind of go through this. For our particular case, we have a lot of design challenges. As I mentioned, we are going supersonic in a 50-kilogram package with a team of really great, ambitious students. We've had about 60 students over the last 4 years working on different aspects of this design. And so part of it wraps into student training, part of it wraps into design modification and understanding, and some of it just understanding just different tools and things that students need to become productive members of the engineering community. So, our design doesn't necessarily fit into the nice package sense that I'd like to believe it is, in a sense where we put it all into a bunch of software and churn the handle a bunch of times and got an answer out. So multidisciplinary design optimization, especially in the team sense, becomes more complicated as well. But a few of our design features and challenges here, you see, aerodynamically we have a low drag Sears hack fuselage design, a pitot inlet, which is a really great inlet up to Mach 1.4. It's not initially great for our entire fuselage and packaging, but it makes a great design feature, especially for a team that's learning as they go. Control system, we have what you see in this picture is a tailless vehicle, so we're using a thrust vectoring nozzle design that we've been developing here as well. And so now it's not even just kind of a trivial sense of aerodynamics. Of course, controls is always the statics, the dynamics, the feedback. And so this is an important part of design that's maybe left off, even though I showed it up in that original system diagram early on in the talk. Landing gear is an important piece. In this case, we're taking off horizontally. How do we take off horizontally with a small wing? We can go really fast, like I say more standard aircraft design, but as soon as you shrink it down, we are well outside the range of off-the-shelf landing gear, so we're custom gear. Our wheels end up being about 4-inch diameter. We can't do 120 knots on the ground, which is what our system would really like to do, so it becomes another really well-focused design challenge. How do we balance good aerodynamics for cruise and minimum drag for takeoff with sufficient lift? Propulsion system, ours is a custom design. I'll show you some details. Structures, so aerodynamics in place is probably where all aircraft starts. Then we maybe talk about, some aspects of controls and structures. The structures is the hard one. Structures we come up with approximations. What's a mass fraction? What are some good requirements or maybe even desirements of where these things should sit? And then how does that finally, when we finally get into the detailed design, can we actually achieve that? And so that is really the challenge that aircraft has. And so you see for our wet mass budget here, we're holding out of our 50 kilograms of 20% of reserve. There's a lot of unknowns that go into this system, a lot of things that we know fairly well, a lot of things that become part of the modeling uncertainty, and of course a good reserve is important. So kind of going through the details, as we just mentioned, this is a snapshot of our vehicle system, a bunch of different CFD conditions, Mach numbers, angle of attack, kind of a small snapshot of cases that we ran, put in the Tecplot Chorus, where we can now visualize them together. I can extrapolate, or I can pull a surrogate model out of this tool to understand my design space. I can actually look through each one of these designs and find a unique design feature, replicate the plot through all of my different data sets, and then visualize it again. Tecplot Chorus has been a lifesaver to us in a sense that it lets us pull through a lot of data very quickly. Now we can do this, I'd say, ad hoc, offline. We can pull up one figure, look at it. We can pull up another figure, look at it. We can kind of do some back of the envelope or some analysis through our data sets and churn it through our own post-processor and come up with some answers. This way is much more efficient. I can look through it. I can understand it. I can see what I'm doing. I can pull, or I can look through for data features in all my data sets simultaneously. And for that, it is a joy to actually do design. But this is kind of, I'd say, where we always start. Aerodynamics is the first place for aircraft design. Once we get into more details, if we're going to design a propulsion system, which we have been working on, we have our own simple analysis, a very simplistic, back-of-the-envelope, classroom-level Brayton analysis. We can go to a different feature with some different levels of fidelity, or then we can get into things like thermomechanics, rotor dynamics. And again, we have, even within one subsystem, our own little cursor dimensionality. Where do we focus our time, effort, resources? Where's the big payoffs? Some of this comes down to that understanding of the system and subsystems, and some of it comes down to the surrogates that are going to help look through our design. So the aerodynamics of propulsion, this is a good place. This is where design starts. Come up with something that looks like this, an excess power plot that says, well, here is our position in terms of Mach number altitude that we can achieve given this matching of aerodynamics and propulsion. And it makes us feel good. We say, well, we're aiming for Mach 1.4. We have some regions here that are looking good. We have some design features we can probably improve on to work on this design construct. So we're pointing in the right direction. And that's a good, I guess, a fuzzy, warm feeling as a place to start, but there's still more to work on. Go through a constraint analysis like this, and this one, in terms of wing loading. So now we're kind of bringing in some of the structural aspects, the thrust loading, some aerodynamic maneuvers, transonic push, cruise, turn, subsonic turn, landing approach, takeoff roll. All these things constrain our design one way or another. So this is a very good, I would say, textbook level analysis of how we understand design, aerodynamics, tying with propulsion, and coming up with, I'd say, where aircraft design sits. The next step is where probably most aircraft design never really gets to, I say, especially in the academic sense, is, obviously if you want to do structures doesn't facilitate itself well to a very simplistic analysis. It's either a mass ratio, or we're going to push through to some more detailed modeling. Once you do detailed modeling, you need to know some very specific design features. So also we've gone to low fidelity aerodynamics and propulsion in a sense, and now high fidelity ANSYS of the structure. We did some high fidelity of the engine as well. But going through this detailed analysis, now we have to understand how these pieces put together in a meaningful way. If we want to go through a lot of design perturbations, we better have a good way to not only do this analysis, as well as to kind of model our way through it in a surrogate sense, so we can extract from this the most important design features and help to do some optimization. And of course, internally, then there's the other aspects. That we look at something like maybe data wiring. Where's our telemetry? Where's our power? What has to go where? So it seems like if we look through this system, we can go through a lot of detailed analysis and design, and it feels very good. We feel like we've done a good job, but unless we go through the testing side to compare, of course, we don't know what we've done. I'm getting a question here about audio. I am using the computer audio, and hopefully it's coming through pretty clear. I did have an error early on, but it seems that it's gone away, so if it's still not coming through clearly, I can transition.
I don't think that'll be necessary, Ryan. We're hearing you loud and clear. So.
Okay, thank you. So if we look at testing, of course, now we're going to build a model. It's not going to look exactly like our system. We're going to want to do some testing, create some Schlieren images. In this case, the Air Force Academy was very gracious to let us do some testing there. In the end, we've done a lot of modeling, so testing is great, but unless we can go backwards and now pin it to our modeling and say, hey, at least our modeling is matching our testing, which is matching hopefully our surrogates. Now we can use our surrogate to do a much more rigorous design optimization because we have a lot more detail and we've kind of hopefully pinned it in a few right cases. Similar for propulsion, we've done a lot of propulsion testing here, a lot of propulsion design. You see a few of our sub-projects that we've been running over the different years looking at different components of afterburners and nozzles and thrust vectoring and biofuels and the works. Anything you could think about we've probably played with at one point or another. But in the end, this comes back to, we need to put this into our aircraft. Our thrust to weight of our entire system is about a 2-to-1, so it gives us a nice place to sit. Kind of wrapping it back up now, we need to put all these pieces together and integrate. Oop, I've lost my picture. Oh, there we go. So this is kind of where we start. We have an aerodynamic configuration. We've done some good work. We've modeled our propulsion. We've modeled our electronics. We've modeled our structure to some degree. And it kind of has this kind of nice looking feel to it. We've done a good job. But the hard part is what happens when you actually want to integrate. Where are those landing gear going to fit? We have to obviously do a landing gear analysis to make sure we get the right angle of rotation on takeoff or on landing. This kind of odd configuration, they have to fold up and fit in somewhere. That comes into mass balancing and CG, which relates to our aerodynamics and control. In this case, you see our servos for the back elevons are way up at the front. Packaging and design, this is where I'd say design is somewhat left off. Design gets us to a point. Once you start going through integration, it's a little bit bigger headache, I would say, in terms of where does everything go? Can you actually fit it? Is it going to balance the way that we anticipated it would? And can we make some sense of this system? In this case here, how our landing gear actually going to fold up into our system. As I mentioned, our gear is custom. You see, some very intricate folding. Our front wheel has got to turn up into our belly to make it fit. And so this is, I'd say, the challenge between good design theory and modeling that we teach, and then the practical aspect of actually what it means to design and build. And of course, the final step is manufacturing. Here's the problem. Manufacturing is a dirty, messy event, and here's a large series of pictures to go from kind of the model and the molding up front all the way to number 15 at the bottom corner of here's what the shell looks like. Hopefully the shell looks like what you thought it was. Sometimes there's imperfection in manufacturing that fold back into design. So, in the end, you hope you've designed in a space that has some sort of robustness to imperfections, to changes. Now, if you're doing pure optimization, sometimes it's very easy to get tricked into something that's truly optimal but completely horrible for a practical sense because it's so sensitive to any perturbation that you're going to be on a cliff no matter which direction you turn. So here's at least our final vehicle. We're still going through integration testing, but looking through the future of design, we're not done our design yet. A lot of our experience with our students is training on design, training on construction, training on flight test engineering and flight test preparation, and so we don't focus on one or the other. And of course, a lot of our graduate degrees are focusing on really the fundamentals of the tools. But design is a challenging piece, and I think we're never going to get to complex configurations like this or others that are much more complex without the benefits of surrogate modeling. So, in a wrap up here, I'm going to just go quickly. Here's our test. We have a lot of things. In terms of short-term, where this really fits back into for us is back to validation. We're validating our low-fidelity tools. We're validating our high-fidelity experiments and computations, and then we're going to, in the long term, go back and go through a critical design review once we get through flight tests and kind of pin some of our models in place a little bit better, and then go through one final design revision. So I did mention Tecplot Chorus here. Tecplot Chorus has been truly valuable to us to get this level design space exploration, surrogate modeling, being able to understand, as a long-time Tecplot user myself, I've always found a lot of hidden data in any particular plot or something I've generated I've gone through and created 6-dimensional data plots using Tecplot, which is phenomenal. But now when I put it in coarse and I can create surrogates and all these different things and make some interesting predictions and extrapolations based on a lot of different data sets, it really helps us do our job well. So I think that's really it. The bottom tagline is really, I guess the key is complex system design is really not possible, I guess maybe especially efficiently without surrogate modeling and effective surrogate modeling design. So I think that wraps up.
Thank you, Ryan. We do have time for a few questions. Thank you for a very interesting discussion, especially in your use of surrogate modeling. Scott and I have a couple of questions, but for the audience, you should see a question dialogue as part of your GoToWebinar sidebar. If you could, if you want to ask a question, there are 2 ways you can do it. You can raise your hand. If you have audio, we can go ahead and open your audio up and you can ask a question. Or if you like, you can actually type that question into the question dialogue and we can go ahead and answer that as well. But I wanted to start with, I think Scott and I had a couple of questions. I'm going to start with Scott's question, and as we're doing that, if you could go ahead, we can talk about some other questions. So, Scott?
Yeah, Ryan, you were using high fidelity and low fidelity models. Can you speak to the ratio that you used for the aerodynamic design? Ratio of low fidelity to high fidelity, for instance. And
well, yeah, sure. For some of this work, so I say for most of this work, we focus really heavily on very conceptual level design, which means we want to do rapid understanding of our design space and go through a lot of system tests. So we do a lot of really low fidelity design, which is why our approach, our place of, I'd say, interest is how do we pick, say, a wing model, for instance, in that realm, understanding where, why, and how it's wrong, and use that kind of place it back into the low fidelity modeling realm, even though it's corrected. But then the high fidelity side, we want to minimize that. Like any other, especially I guess a university, we are resource limited for computations, and limiting the number of inputs is important. So I would say probably in the end, our ratio is, I don't know, maybe 100 or 1,000 to 1. Low fidelity to high fidelity is hard for me to say, but it's pretty extreme.
Okay. We do have a couple of other questions. One in particular about how long has this project been, or what has been the duration of this process?
Well, it's a little bit muddled in the sense that we started off working strictly on propulsion system design, which is still ongoing, but we spent about 2 years on propulsion system design, and somewhere near the end of that we started working on the vehicle design. So the vehicle design and construction process here we've been working on for all told about 2 years as well. I guess I'll pin that with 2 academic years. We generally have no students here, so we take summers off.
In terms of the you had talked about this extreme ratio of high fidelity to low fidelity. In that context, what was the average solution time perhaps for your high fidelity simulation, and if you know or happen to know what the time was typically to run your low fidelity simulations as well?
Well, the low fidelity essentially is in the order of seconds. Pretty simple tools to do pretty simple approximations. And then the high fidelity is like depending on the models, the aerodynamic models we can run on a single processor, one, say, CFD solution, in a simple sense, maybe in an hour or on a couple processors, excuse me. So, our examples are somewhat not to the major extremes of, I'd say, true rigorous CFD that's really, we haven't gone and embraced a large eddy simulation through a combustor, for instance, and they're really extreme. So ours are a little bit more benign comparisons, but when you're running computations on the order of an hour and you want to map out a design space and then map out a performance space, it's a lot of computation still.
Okay, we have time for maybe 2 more questions. Scott has one as well, so if there are other questions, feel free to type them in. Scott?
Well, back to my previous question, it sounds like early on in the process you use a lot of low fidelity models, but as you're going towards the end and you're building your final surrogates for the aerodynamic design, I mean, does that ratio hold, or do you go to do more high fidelity in that at that stage?
Oh, sorry. I see. Yes, definitely near the end, we're doing a lot more high fidelity because now we are trying to, I would say, hone in and understand the true performance of the design that we've really focused in on. And so now we're looking at trying to understand our design tools and where they've made, where those sources of error may be. And so there's a lot more high fidelity data, I would say, in the current cycle than it was in the beginning.
Looks like we have another question.
Yeah, the question is around the times for the CFD runs. Was it done in parallel processing? I wonder if that's in the context of doing that across collections of CFD results, and how many nodes do you use, I guess, is the other question. So maybe you could describe your computational resources. You said you ran on one node, but maybe you can...
Oh, yeah. So we do have a number of resources here. Small research cluster, 128 processors. We do also have access to, say, our campus supercomputer, I think is 16,000 cores, but the problem is as soon as we get into proprietary software and some other issues, we do have problems getting things on there. For software that we've developed ourselves, it's definitely not a problem, but sometimes when we have to worry about a cost per node for, say, a CFD solver, then we have to worry about how we get extreme. But yeah, we definitely have not run this on the extreme cases. We've kind of tried to minimize, through smart design and modeling, the number of computational runs we need. And so the smaller resources have been sufficient for now.
Okay. We have time for one last question. So I'll give, if anyone has an additional question. If not, I do have a question myself. One of the things that we talked about, or you talked about earlier, was estimating error and using co-Kriging. Do you have, or what mechanism were you using to estimate that error when you were doing the co-Kriging, and were you using confidence interval or some other mechanism to understand that error as part of the process?
Yeah, so the one that I was showing here, actually we did not use co-Kriging. Co-Kriging is a good way to put low fidelity and high fidelity data together, which is still the same goal. Our explicit goal, at least in that example, was to extract that error. So for us, we quantified the error as use the high fidelity as being the correct, which is of course not always the best way to go. But for that example, we assumed the high fidelity was modeling physics that the low fidelity was missing, and we assumed that one to be more correct, and so we use that as the source of error. But definitely going through an uncertainty quantification on that process is where we are now to do a little bit more rigorous job of the statistical nature of the error.
Well, excellent. We're pretty much out of time. If those people who may have additional questions, Ryan, do you have how would they contact you if someone wanted to learn a little bit more about the work that you're doing?
You can either through email or phone, and I think it was on the original announcement, but email is rstarkey, S-T-A-R-K-E-Y, at colorado.edu, or you can check out our website and email me through there, or my phone number is there as well, www.colorado.edu/Busemann, B-U-S-E-M-A-N-N.
Great. Well, again, I wanted to take this opportunity to thank you, Ryan, for a really very interesting conversation, and thank you again for showing how Tecplot Chorus plays a role in it, and thank you, Scott, for sitting in as well.
Yes, thank you, Ryan. That was an excellent presentation.
We will have this recording available probably by this afternoon. And again, if you have additional questions, please feel free to either contact Ryan directly or to send them our way. Thank you again.
All right, thank you.